Hi, I'm Brandy Heflin. I'm a personalized physics instructor, and I help high school and college students feel confident and successful in learning physics. I'm here today with part 3 in my 4-part series on data handling, analysis, and interpretation for introductory physics labs. In part 1, we learned about interpreting slopes and intercepts. In part 2, we learned about linearization and other kinds of relationships that aren't linear. And today we're going to learn about constructing mathematical models of physics data. A mathematical model is the equation written in slope-intercept, or y equals mx plus b format, which describes the relationship between the two specific physical quantities that were measured and plotted in this lab. Constructing a mathematical model needs first the linearization of the raw data, and then determining the slope and y-intercept with appropriate units. Once you've plotted the raw data, the rest is easy. In place of y, we will put the dependent variable for our data. And then m is the slope with units. In place of x will be the independent variable for this data set. And b is the y-intercept with units. And a key step in this process is using an appropriate symbol for each physical variable that you measure and plot. The symbols and units should be used when plotting the data as labels on the axes. The symbols alone should be used when constructing the mathematical model, and the units are used on the slope and y-intercept only. Take, for example, this weight versus mass data from video 1. We found in that video that the slope of this data is 2.205 pounds per kilogram. So to construct this mathematical model, we will take the symbol for our dependent variable, w, and that will be equal to our slope with units, 2.205 pounds per kilogram. And then we will multiply that by the symbol for our independent variable, m, for mass. So this relationship is saying the weight of an object is equal to 2.205 pounds for every kilogram multiplied by the mass of the object. And of course, since our intercept is 0, I could go ahead and write in plus 0 pounds, and I'm putting it in a different color because it's optional. So if you feel a need to be complete with your model and include an intercept of 0 with units, you can, or you can leave it off. And also recall from video 1, this speed versus elapsed time graph. We found in that video that the slope for this data set is negative 0.8 miles per hour per second. So here, to construct our mathematical model, we can take our dependent variable symbol, v. That will be equal to negative 0.8 miles per hour per second multiplied by our independent variable symbol t, and then we will add our y-intercept 20 miles per hour. And what this model says is that the velocity of this moving object at any point is equal to negative 0.8 miles per hour for every second multiplied by the elapsed time plus 20 miles per hour. And from video 3, we have a top opening parabola. In this case, this is the position versus elapsed time data for some moving object, and I've included the table for you to take a look at as well. So when we linearize this data and plot it, we will plot the elapsed time squared, and we will use the appropriate symbol of t squared on our graph and the units of seconds squared, and we will add time squared, not just time, into the title of our graph. So here's this model. This x here means horizontal position. So this is the horizontal position of some moving object. And so even though it's the y-axis and it's y that we're replacing in y equals mx plus b, in this case, x is meaning position. You might recall from video 2 that the slope we found for our top opening parabola was 2. I did use the same data set here. And then we didn't have units before because we were just dealing with numbers and not actual variables, but from video 1, we can see that these units will be 2 centimeters per second squared. And then last but not least, we will use our independent variable symbol t squared. Our intercept is 0, so we can leave that off. And this model is saying the position of this moving object at some point in time, at any point in time, is equal to 2 centimeters for every second squared multiplied by the elapsed time squared. And here we have the velocity versus position for some moving object, and you can see it's a side opening parabola. And again, I've provided the data for you to take a look at as well. So when we linearize this data set, we are going to end up plotting velocity squared, because it's a side opening parabola, our vertical axis variable squared. And here on this chart, we've used the appropriate symbol v squared for our dependent variable, and the units of meters per second, the whole thing squared becomes meters squared per second squared. And of course, we've put velocity squared in the title. So here, our model becomes dependent variable symbol v squared equals, I've used some other software to find that the slope here is 8. And let's take a look at these units. We're going to do the vertical axis variable units divided by horizontal axis variable units. And that looks a little strange. Meters squared per second squared for every meter is easier to interpret, but it does look easier or prettier when we cancel out 1 power of meters and are left with just meters per second squared. So we'll put that in our model, 8 meters for every second squared. And then our independent variable symbol, and our intercept is 0. So this model is saying that the velocity squared of this moving object is equal to 8 meters for every second squared multiplied by the position. And last but not least, we have one of our inverse relationships. In this case, it's the acceleration of an object versus its mass. And as always, I've included the data table for you as well. And here we are going to plot the inverse of mass on our horizontal axis, because that's what the shape of our raw data graph suggests. And I've included the proper symbol 1 over m, or 1 divided by m, and the units of 1 per kilogram to go with this. So here is our model. We will take the dependent variable symbol a, and I've used some software to determine that the slope of this data is 10. But let's talk about these units. We're going to have meters per second squared over 1 per kilogram. And again, that might actually be easier to interpret with the process that we discussed in video 1, but it will look prettier and easier if we remember that dividing by a fraction is like multiplying by its inverse. So we can take our meters per second squared and multiply it by kilograms over 1 to yield final units of kilograms times meters per second squared. So we'll put our kilograms times meters per second squared up here for our slope, and then finally we will put our independent variable symbol. For this chart, our intercept is 0, and this model is saying the acceleration of this moving object is equal to 10 kilograms times meters for every second squared multiplied by the inverse of the object's mass. So I hope you've enjoyed today's short lesson on constructing mathematical models for physics data. If you hadn't watched video 1 on slopes and intercepts and video 2 on linearization, I encourage you to go back and do those now and then revisit this one. If you'd like to connect further, you can reach me via email at brandyheflinphysics@gmail.com. You can also visit my website, virtualphysicsofficehours.com, where you can schedule a free needs assessment to claim your free first session, and you can also check out additional free help options if you're not ready to commit to some one-on-one tutoring right now. You can also find me on Facebook at Physics Tutor Brandy. I love physics, and I love helping you. Until next time.